Welcome to the routing and distribution and route planning lecture. This is part of the transportation module, and it's one of the most important topics in the transportation module. Why? Because distribution costs are often a large part of your transportation expense. Okay, so what are we going to be talking about today? We'll be talking about the last mile problem in logistics, which refers to the lost leg in the delivery of a product to the customer or end consumer. Okay? It is often the least efficient link in the supply chain because you have to travel to many destinations to deliver product to different customers' homes or facilities. So you might have heard this term hub and spoke model. This refers to the fact that you have these hubs. You could think of them as distribution centers or processing facilities. And between the hubs, you do these efficient transportation. You send truckloads or rail car loads, and you can move product, let's say, from your East Coast distribution center to your distribution center in Texas very efficiently. So these are the hubs. Okay. But once you are in a particular state or region, and then you have to distribute product to hundreds of retail stores there, or hundreds of thousands of end customer addresses, then that is not as efficient, because you have to drive long distances for small deliveries, and that is the problem that is called the last mile problem. Distribution, when we say distribution in this module, in this lecture, we are talking about outbound transportation from a company's facilities to either end customers, end users, or to retail locations. Okay. Selecting efficient routes is crucial to keeping your distribution costs in control. So in general, there are three types of problems. Okay. The first one is you have a single source and a single destination, and you have to move product from point A to point B. Okay. This is the easiest type of problem to solve, because you just find the shortest path from point A to point B, and you move product using trucks or rail or whatever transportation mode you want. Okay. Then you may have a situation where you have multiple sources and destinations. So for example, you may have inventory in multiple warehouses that needs to be moved to multiple retail stores. So you have many source points and many destination points, and which source should supply which destination then becomes a question. Okay. The third type of problem we have is where you have a delivery route or a collection route that is going to have the same starting and ending point. So think about a distribution center. Your truck or delivery vehicle will leave the distribution center, connect with multiple customers, dropping off goods or picking up goods, and then come back to the distribution center. So this is like a milk run where your starting and ending points are the same. We're going to spend most of the focus of today's lesson on the third type of problem, a milk run type of problem, where your starting, origin and destination, the final ending points are the same. Okay? And there are two versions of this problem that we'll talk about. One is called the traveling salesman problem, or TSP, and one is called the multi-vehicle routing problem, MVRP. And so we're going to look at how do we solve these problems to come up with efficient routes. Before we start the third one, let me give you a brief picture of what does the second type of problem look like. Okay. So here's a picture. Okay. You have multiple suppliers, and they all have a capacity. So this supplier can supply up to 700 units. This supplier can supply up to 500 units or less, and so forth. And then you have multiple destination points here which need that raw material. So in this case, there are production plants, and they have certain requirements for raw materials. And then you have multiple paths. From each source, you have a path to each destination. And then there's a cost to transport product on these paths. So if you send 1 unit from supplier C to plant 1, you're going to spend $9 per unit to transport those units to plant 1. And so the question is, how much product should flow on each of these paths? Or in other words, this supplier should supply how much to each of the 3 plants, this supplier should supply how much to each of the 3 plants, and this supplier should supply how much to each of the 3 plants. This is on the inbound side of the supply chain. You could have the same picture over here where you have manufacturing plants feeding distribution centers or retail outlets. Okay, same idea. You have multiple sources, multiple manufacturing plants. Which plant should ship how much to which DC or retail store? These types of problems are solved by optimization models that we'll look at in the network planning or logistics network design module. So we will do some optimization models which can solve problems like this, because usually when you are trying to see where should you locate your plant or how many plants you should have in your network or a warehouse or a DC, you have to solve a problem like this, which looks at the inbound and the outbound transportation for different locations, and tells you, like, if you locate a plant here, it's going to be optimal for you versus locating it somewhere else. So a very similar problem is solved when we are designing a logistics network. So we're not going to talk about this problem today. We will come back to it when we talk about logistics network design. Okay, so let's look at delivery routing, which is that milk run problem. Okay. First, we're going to look at the simpler version of that problem, which is sometimes referred to as TSP or traveling salesman problem. The question we're trying to solve is something like this. We have a list of destinations. They could be cities, they could be customer address of different facilities. So we have a list of destinations, and we know the distances between each pair of destinations. Okay? So we know if you go from facility 1 to facility 3, what's the distance? If you go from facility 2 to facility 5, what's the distance between them? If you don't know the distances, you can easily find them using something like Google Maps. You can put in those addresses and find the distances between addresses. What is the shortest possible route that visits each destination exactly once and returns to the point of origin? So you start from the point of origin, you have to visit each destination exactly once, and then you have to return to the point of origin. It might sound like, well, that should be easy to do. You just leave, you just hit the point and you come back. But to find the path which minimizes your distance traveled is not trivial. This problem has been found in books written hundreds of years ago, but till today we have no algorithm that can guarantee the optimal solution in a short amount of time. We have a lot of good algorithms which can give you very good solutions in short amount of time, but those solutions are what are called heuristic solutions. They are good solutions, but we are not guaranteed that they are the optimal solution. Okay. So we encounter this problem in logistics when we have one vehicle which has to go out and deliver product or pick up product from different customers. Let me show you an example of what the problem and the solution looks like. So this is a problem where we want to visit 48 states. Okay. 48 states in the contiguous US, geographically contiguous 48 states. In those 48 states, we're going to visit 50 different landmarks or monuments or national parks, things like that. Okay. So what's the shortest trip possible? What is the shortest distance we can drive to hit those 50 monuments or landmarks and come back to where we started from? So this is a classic traveling salesman problem. Okay. If you want to visit 50 landmarks, there are 50 factorial possibilities. 50 factorial is 3 times 10 to the 64, which is a huge number. So there are a huge number of possible routes that can connect those 50 landmarks. And if we could list all of those routes and calculate the distance for each of those routes, then we could easily pick the shortest route. But the problem is it will take a computer, a very, very long amount of time to be able to list all of those 50 factorial routes, just because there's so many of them. Yeah. So we're not going to list all of them. We're going to use a heuristic algorithm that can give us a good solution in a minute or two, instead of waiting years for the solution. And all of these heuristic algorithms, the way they run is they want distances between every possible pair of points. So if you have 50 landmarks, you make pairs, okay? So that's going to be 2,500 pairs, A to B, A to C, A to D, D to B. And then you want the distance between each pair. So so the algorithm knows if they are at a particular landmark or a particular site and they want to go to a different site, what's the distance they need to travel. Once you have that distance table, a matrix is just a table. Once you have the table of distances between pairs, you can run these algorithms to find a solution. Okay? Now this is why if you try to make a route in Google Maps, it limits you to 10 via waypoints. So you can't have like 50 addresses in Google Maps at the same time and tell Google Maps to find you the best route which connects the 50 addresses. It will only let you do up to 10 because it takes a lot of computation to go beyond 10. I mean, Google Maps could use a heuristic like the one I'm going to show you to do way more than 10 as well, but then it will not be guaranteed optimal solution. It will just be a good solution. This is what the solution looks like using a class of algorithms called genetic algorithms. So we will not be running these algorithms. You need to know how to do computer programming to run an algorithm like that. There are software which can do this for you. I might give you a link on Blackboard to one of them if you want to play with it. But these algorithms are built into software, few of which are available for free. Okay, but most of them you have to pay for. And so those algorithms can give you an answer like this, where it tells you, what order to visit these sites in, which gives you a short route. Okay? So this is an algorithm run by a graduate student, Randall Olson, for about a minute. After about a minute, the algorithm gave a route of 13,699 miles, which goes over 48 states and hit 50 landmarks in those 48 states. There's an extra stop added right here in Cleveland to make sure that we don't go outside the US, because otherwise the shortest distance between Vermont and Michigan passes through Canada through the Ontario province. So to make sure we don't go into Canada, that was one of the requirements of the problem, that we stay in the US. A 51st spot was added in Cleveland, but we're not really stopping in Cleveland. Okay. Assuming ideal conditions, you could do this route in 19 days if you drive 12 hours per day. But if you are going to be stopping and sightseeing, it might take 2 months or more to complete. Okay. So this is a great idea if you are thinking of what to do over summer. You can take this route and go see the United States. Somebody else did the same thing for Europe. So this is 50 landmarks to visit in Europe.
You
can see that you have to take the ferry sometimes. You have to go over water, especially when you go to the UK, because UK is separated from the rest of Europe by water. But you can take ferries, you can drive a car onto a ferry and the ferry will take you across.
Which is
so you can still do this in your car.
Now I wouldn't like 12 hours.
So let's look at some simpler heuristics on how to solve this problem. The first one we're going to look at is what's called the nearest neighbor heuristic to solve the TSP problem. Again, remember, what is a heuristic? Heuristic is an algorithm which gives you a good solution very quickly, but the solution is not guaranteed to be optimal. It's usually a good solution, but there's no guarantee that no better solution exists. In many times, a better solution is there, but the heuristic could not find it because heuristics do not solve the optimal solution, because that will take too long. You're trading off time for optimality. So you're saying, I'm going to spend less time solving the problem, but I'm happy with a less than optimal solution. Okay? So there's a video here which shows you how to do this simple nearest neighbor algorithm in detail. You need to know this for exams and homework. I'm going to show you an example in the slides as well, but I highly recommend you also watch this YouTube video. Okay, so here's the nearest neighbor algorithm. You start at some point and mark that point as visited. Then you jump to the shortest point, the shortest next point from the point you are at, which has not been visited before. You jump to that point, you mark it as visited. If there's still more points remaining, you continue this step. So let's look at this example. Okay. We have 5 points, A, B, C, D, E. We have to visit all 5 points. Okay. We're starting at point A. So if you are starting at point A, you can look at which point is the closest to point A. Point B is 500 units away, so that's not the closest. E is 205 units. D, which looks really far on paper, is only 185 units away. So starting at A, the closest next point is D, so you will go from A to D. So A has been visited and D has been visited. Now at point D, you'll find your closest point. You don't go back to A because A is already visited. You only look at the unvisited points. So look at E, C, and B. Well, E is 320 away, B is 360 away, but E is only 302 kilometers or miles away. So we're going to go to E. Okay, and we're going to mark E as visited. So now only 2 points are left, B and C, which are not visited. So from E we check, okay, B is 340, C is very close, it's only 165, so we go to C. From C we can only go to B because everything else is visited, so we just go to B and then we go back to A, because you have to end at where you started from. You have to have a complete milk run. So once all points are visited, so at B everything has been visited, then once everything is visited, you just return back to the starting point. Okay? So the route we get is using nearest neighbor, A to D to E to C to B to A. Okay? Notice that the route starts at A and ends at A. The total distance traveled, we can just add it up. The first journey is A to D, so you take 185, plus you have to go from D to E, so you take 302, plus 165, which is E to C, plus 305, which is C to B, plus 500, which is back to A, B to A. So the total distance traveled is 1457 miles, and we were able to go from A, hit all the 4 points, and come back to A, which is the 5th point. So that's how we do nearest neighbor. Remember that you have to be greedy. You're going to be, which is like lazy in this case. You always jump to the point nearest to you, which is not yet visited. So you don't jump back to visited points, only an unvisited point. Let's do the same problem. This is the exact same picture, but let's say what happens if you start at B. What route will you get? So I encourage you to do this problem. Start at point B and find what route you get from nearest neighbor. So first you're going to jump to C, which is the closest, because D is 360 away, E is 340 away, A is 500 away. So you're going to jump to C first. Then from C you'll jump to E, to A, to D, and then back to B. The total distance of this route is 1220 miles, which is, and you've hit all the 5 points, and this route is much shorter than the route obtained when you started at point A. So starting at point A gave us quite a long route, but starting at point B gave us a much shorter route. So with nearest neighbor, you could get a different length of the route depending on where you start from. Okay? So the route length can vary depending on the starting point. Because nearest neighbor is so quick to run, oftentimes people will run nearest neighbor from all possible starting points. So they'll get route starting from point A, okay, it's 1457 miles. Route starting from point B, that's 1220 miles. You can get route starting from point C, whatever the mileage is. Route starting from point D, and route starting from point E, okay? And then once you get these 5 routes starting from different points, you can pick the route which is the shortest route as your solution. Okay? So let's say we did that exercise, we got the 5 routes starting from different starting points, and we find that starting at point B gives us the shortest route. Okay? But that may not be very helpful to us if our distribution center is at point A and points B, C, D, E are customers. You can't just move your distribution center because you like to start from point B. But don't worry, all is not lost. All of these routes are circles. This is a circle A, and then you come back to A. This is a circle. This is a circle. When you have a circle, you can start from any point in that circle and go to any other point. So for this route, I could just start at A. I don't have to start at B. I could go A, D, B, then B to C, E back to A. If you start from A to D to B, C, E back to A, your distance will still be 1220 because you still did the same circle. So you would still do a distance of 1220, but you'll be starting at point A. So the point is, when you get routes like this, they are circles. Circle meaning they're connected, they go around in a loop. Well, maybe not circle, maybe I should just call them loops, because they don't look geographically as a circle, but they're just loops. So you can move the starting point to any point in the loop and then do the loop starting at that point. As long as you come back to the starting point, you finish the loop, you're going to travel the same distance. So I can take this route, which is a better route than this route, and I can just move the starting point to A. So this route, B, C, E, A, D, B, when I start from A, I'm going to get A, D, B. Then B to B is just no traveling, so B just comes once, and then you go to C, E, and then you return to A. So A, D, B, C, E, A is the same route as B, C, E, A, D, B. And it has the same distance, 1220. You can verify that. You can look at this route, go back to the picture, add up all the distances, and you'll see you'll get 1220, a much shorter distance than here, and you're still starting from point A. So when we use nearest neighbor, we'll often calculate multiple routes to find the shortest route, and then we can move the starting point to whichever point we want, because it's a loop. Doesn't matter where you start, where you end, as long as you do the whole loop. Okay. Usually on the exam, I'll not ask you to do that. On an exam, I'll just say, okay, start from this point and give me the nearest neighbor solution. You don't have to start from multiple points on an exam, but in real life, that's how you would use it. So how good is this nearest neighbor heuristic? People have done studies where they do simulations, they find multiple different configuration of points, and they run nearest neighbor, and then they try to find the best solution possible, and then they compare nearest neighbor to the best solution possible. Okay. On average, nearest neighbor is going to give you a 25% longer path than the shortest path possible. Okay. If you start with different starting points and do all of that extra work, you might be able to bring the 25% down to a lower cost. This is the cost of using a simple algorithm. You're not going to get the best route. You're going to be within plus minus 25% of the best route usually. Okay. If you want to see if nearest neighbor gave you a good solution or not, one way to kind of check is to look at the last few legs of the journey. If the last 2 or 3 legs of the journey have the same distance as the first 2 or 3 legs of the journey, then it is probably a good solution. Probably, we can't be sure. If, however, your initial legs are very short and at the end you're doing these long legs or long jumps, then there might be better routes that exist. Okay. Sometimes nearest neighbor can be a lot more worse than just 25%. There are, you can make a configuration of points where nearest neighbor will do really badly. Okay, maybe I can show you what one of them might look like. So sometimes you have points like this, and the shortest route might be to go like this. Okay, but nearest neighbor will zigzag all over the place and then come back. Why is nearest neighbor zigzagging all over the place? Because at each point, the nearest point is the point on the other side. So it keeps going right, left, right, left, right, left, and up. Then it's going to come down. So you're going to go up, you're going to come down, but you're also going right, left, so you're going to get a much longer route with nearest neighbor than if you just went up and then just came down. Okay, so there are situations, and you can detect that. You'll see that initial, if you go the zigzag route, nearest neighbor gives you the zigzag route, you can see that initial journeys, initial legs are very small, and the last leg is very long. So you know it's not a very good solution. Okay, but it can give you, poor solutions. Okay, let's look at some other heuristics. So this video is going to show you the traveling salesman problem, and it's going to show you how various algorithms can work, and how they kind of give you good solutions for this problem. Okay. Now you just need to have an idea of how heuristics works in general. You don't need to, we're not going to cover all the algorithms shown in this video in detail, because that'll require a full course on just this distribution issue. But you should have some familiarity with the logic behind these heuristics and what are the various heuristics available to you. So we are starting off with nearest neighbor. The greedy algorithm, always choose the next closest city, is also called the nearest neighbor algorithm, which we just covered. So we're going to start with that. Notice it gives you a very bad route, because you can see you're crisscrossing over your own tracks. Whenever you're crisscrossing over your own track, that's usually a sign that this is not a good solution. So in this heuristic, we're going to do swaps. We're going to look at, we're going to start with a solution like a nearest neighbor solution, and then we're going to say, what if we swap the order of visiting 2 of the destinations, and let's see if the new route is better or not. So you do swaps and try to see if the swaps generate better routes or not. So you're starting with a solution and you're trying to improve it incrementally. You can see as we do the swaps, the distance of the route is decreasing, because all this overlapping back and forth, we're going to reduce this backtracking over our own trail, because good solutions are these loopy things which go around, which don't go crisscross all over themselves. So we started with a random solution, which is a really bad solution. If had we started with nearest neighbor, we would be a little bit further along in our way to find a good solution. So usually we don't start with a random solution. Usually we might start with the nearest neighbor solution and then do these swaps to improve that solution. Notice we have decreased the distance by half or more because it was above 40,000. So we have more than halved the distance, and you can see all that backtracking and crisscrossing our own path is mostly removed. There's some left over here, but mostly we have removed that crisscrossing and backtracking over our own path. So simulated annealing is a heuristic which works in some way similar to the genetic algorithm I showed you earlier with Randy Olson's solution for the visiting 50 landmarks in the US. Simulated annealing is a similar idea where you start off with multiple solutions and you improve those multiple solutions, and then slowly you start throwing away the bad solutions and only keeping the good ones. But the idea of simulated annealing and genetic algorithms is don't just work with one solution, work with 500 solutions, keep improving these 500 solutions, then start discarding the worst ones, and by the time you finish, you're left with a few really good solutions. So these are the ideas behind genetic algorithms as well as simulated annealing. Notice as the temperature drops, the number of solutions we are maintaining is dropping. So we are discarding the bad solutions. The picture is showing you the best solution we have right now, but the algorithm has in its memory 100 or 50 solutions it's working on, and at any point in time it's showing you only the best solution it has till that point in time. Okay, now the good news is that human beings can, without any algorithm in their head, if you just plot the points on a map, human beings tend to do a pretty good job at finding good routes. Okay, when the number of stops is small, 8, 10, 15. If the number of stops increases, human beings' performance tends to degrade at that point. But for a relatively small number of stops, you can just plot the points on a map and then just draw out a route. Okay, good eyeballed human solutions will often follow a loopy teardrop or flower petal pattern with minimum crossing or crisscrossing of paths. So you don't want to backtrack or cross over where you've been, and you want to do a loopy pattern connecting the points on your graph paper. This is an example. So let's say this is a depot or a warehouse, and the solid points are customer locations. So you don't want to do something like this where you are crisscrossing over yourself. You want to do like a flower pattern or teardrop pattern connecting the points and coming back. So you can just eyeball it, and you'll usually get a good answer if the number of destinations is small. So that was the traveling salesman problem, but in real life, we often have more than one truck going out to do the deliveries. In the traveling salesman problem, we just had one route connecting all the points, which meant one truck can go out and do the deliveries and come back. But what if the deliveries that we need to do exceed the capacity of one truck? So we can't just send out one truck. We have to send out 5 trucks or 10 trucks or 50 trucks to do all the deliveries. Well, then you don't need to find just one route, you need to find one route per truck. So if you need to send out 10 trucks, you need a route for each truck. So you don't need one solution or one route. Your answer must have a route for each truck that you need to send out. So that is called the multi-vehicle routing problem, MVRP. Okay. The idea is similar to the TSP problem. You have a warehouse or depot or a source point, and you have to deliver product or collect product. It's the same problem either way, from multiple destination points, and then you return back to the original depot or your origin point. The difference here is now that you can have multiple vehicles with different capacities, okay, because one vehicle is not sufficient. You may have time windows on the stops that you can visit certain customers at certain times of the day only. You may be doing pickups and deliveries both on the same routes, right? And you may have often a restriction on the total travel time for a vehicle. So, drivers can't drive more than 11 hours on a truck in a day based on safety regulations and so forth. So you may have a restriction on how many hours can a truck be operating and before it has to come back. Okay. So here are some practical guidelines for finding some good solutions to this problem. One thing you want to look at when you're making these routes is look at this problem right here where we have 2 trucks. So we're going to visit half the customers with truck 1, and because of truck capacity issues, the other half are going to be visited by another truck. One way we can do the routes is to do a teardrop type of pattern of the customers on the left side. So that's one truck goes on the left side, and then we do another teardrop pattern on the right side, and another truck visits the right side. Okay. If we want to evaluate if this is a good solution or not, one thing we should look at is what is the distance between points on the same route. We want the distance between points on the same route to be small. But look here, from this customer to the next customer, we travel a long distance. And again here, from this customer to this customer, we travel a very long distance. So this is not a good solution because between pairs of customers, we have very long journeys. Okay? An alternative of this solution is to say, I'm going to send one truck to customers which are close to me in a loopy pattern, and I'm going to send my second truck to these customers up here in the northern region, which are a little bit far from me. So now if I look at these 2 routes, the distance between customers on the same routes is pretty small, and similarly for this route, once you hit a customer, distance between any 2 customers is pretty small. So we have short journeys between customers. So this is, in general, this will be a better solution than this one. Okay. However, in real life, there are sometimes situations where we will prefer this over this, even though this might give us a shorter distance traveled. Excuse me. Okay. So I encourage you to pause the video and think why, if this is giving us shorter routes, would you ever want to prefer this with longer routes? Now that you've thought about this, let me give you one reason why. We have one delivery team going on this route here at the bottom, and a second delivery team going on the route at the top. Guess which team or which driver gets done first? Obviously, this route will get done first because you're really close to the depot. So this team goes out, they're done in 4 hours of the day, and then they relax and they get paid the same money. And the second team goes out and they spend 8-9 hours of the day doing their work, and they get paid the same amount of money. The team which has to work 8-9 hours to get the same money is not going to be happy, and the team which only works for 4 hours and gets the same amount of money is going to be much happier. So there's going to be conflict where everybody will say, I want this route. Well, you could swap teams and say, okay, today you get the shorter route, tomorrow you get the longer route. So you could swap the routes around on a daily basis. But the point is, if you have routes with very different workloads and different distances, that can sometimes create conflict. Yeah. Sometimes it's not that people want the shorter route. Maybe there's overtime to be had with this route, because this route being longer takes more than 8 hours to do, and additional time beyond 8 hours you get paid overtime. So everybody might want this route so that they can get paid overtime. So once you have these sorts of situations, there's a chance for conflict, and you have to manage that conflict somehow. In this case, both routes are very, very similar because they are the same distance and probably are going to take the same time. So you're going to have less conflict here. I mean, if this is obviously better from a distance perspective, and if you can manage the conflict, you'll go with this. But sometimes, just to keep things equal, you might prefer something like this over something which is a little bit more optimal. Sometimes you have different days. So let's say you have 5 groups of customers or retail stores. You hit one group on Monday, another group on Tuesday, another group on Wednesday. Again, same idea. Look here. F is the customers we hit on Friday, and T is customers we hit on Thursday. So you can see that the Thursday and Friday routes overlap. I mean, if you are going here on Friday, then you're going past the same area on a Thursday. So you're hitting this area twice in a week. This is not good. You should either visit these customers on Thursday or Friday. This here is a better solution, where you go here on Friday and you go there here on Thursday. There's no overlap and crisscrossing. So if you can avoid overlap, crisscrossing, you're usually going to end up with better routes. Okay. So obviously, the customers now, these customers were being hit on Thursday before. These customers have to agree to being served on a Friday, and these customers were being hit on a Friday before. They have to agree to be served on a Thursday. So you have to work with your customers, but if you can do that, you can have better routes. Some other guidelines, if you're building routes manually, build routes starting with the furthest stop from the depot. So add the faraway stops if you have multiple faraway stops close to each other on the same route first. If you have only one faraway spot, then you should consider serving that with a separate truck. So look at point 7. A stop that is greatly removed from a route cluster is a good candidate for an alternative means of delivery. So you might send a small truck just to do that one faraway spot, which is nothing, no other customers near it, or you might just outsource that delivery. So you can look at these outliers separately. But if you have a cluster of stops which are far away, but there's more than one stop there, then you want to start building a route from that. You also want to start building a route with the largest vehicles first, and the stop sequence in a route should form a teardrop pattern if you don't have time windows. If you have time windows, you may have to modify, and you may not get a teardrop pattern. And we don't like time windows usually because they give us inefficiency. You can't follow the most efficient routes. But if you have to have time windows, then this may be violated. You want to mix pickups and deliveries rather than going to the same area twice, one for pickup, one for delivery. And you should try to avoid narrow stop time window restrictions, because they would give you very inefficient routes in terms of distance traveled. Okay, let's do an example to apply all of this. So in this example, I'm going to show you that just following these guidelines, point 1 to point 8, and just plotting your customers on a map, you can come up with some pretty good, efficient routes manually without requiring complex algorithms or software. Okay? Now, this is going to be useful if your customers are stores or warehouses which have a fixed location and you're going to be hitting them every week or every day or every month. If your customers are, like, let's say people at home ordering stuff online, then each week you'll get a different organization of addresses. Some week, you're delivering to certain addresses, the next week you're delivering to other addresses. So if your destinations are changing day to day, week to week, then you have to invest in a software solution which can do the routing for you. But in many B2B cases, business to business, let's say you're delivering spare parts to car dealerships. The car dealerships are the same dealerships in your area. You have to deliver to them once a week or every day. They're not moving. If you're delivering to retail stores, to gas stations, things like that, then you can do your routing just on a map with pencil and paper. So this is such an example. This triangle in the middle in Lansing is our warehouse. So our DC, distribution center, is in Lansing, Michigan. And these dots are our customer sites. Our customers are funeral homes, and we're going to supply them with caskets. Okay? Now, based on the demand of these funeral homes, we need to give them a supply of caskets once a week. Okay? So that actually helps us out, because you can see there's a lot of customer locations. Okay? But we only have to visit a customer once a week, which means if we are going to be working 5 business days, Monday to Friday, then I can divide this region into 5 regions, and I just have to do 1 region a day. So I do 1 region on Monday, another region on Tuesday, another region on Wednesday, so forth, and then I start again the next week, and I hit each customer once a week. So think about how would you divide up this map into 5 regions so that they're about equal in terms of demand, and then you can hit each region 1 day of the week. So how should I divide this into 5 regions? Should I divide it by doing a line in the middle, a line like that? That will give me 4. Should I do like pizza slices? Should I do concentric circles? What should I do? So think about that for a minute, pause the video, and then I'll show you one good solution. This is not the only good solution, but I'm going to show you one good solution. Okay, so this is one way to split it into 5 regions. Okay, so we have 1 box around our warehouse. And then, so this is the central region, and then we have 4 other regions around it. Notice there's a lot of demand in Detroit, so we have split Detroit into 2 regions. Why? If we put all of Detroit into 1 region, we may need a lot more trucks when we have to serve Detroit, and then some of our trucks might be idle on the days we don't serve Detroit. So you want the demand in a region to be approximately the same size or volume. So the volume of this region here should be approximately the same as the volume of this region, as the volume of this region, as the volume of that region. So that is why, to make the volumes match up, we are splitting Detroit into 2 regions and drawing a line through Detroit. Okay. Now, why do we have a central region like this? Think back to this picture right here. See, you don't want to be driving to a customer close by to Lansing and then driving to Grand Rapids or something, or somebody really far away on the same route. You want to do all the customers close by on a separate route, and you want to do all the cluster of customers which are far away on a separate route. This is a better routing than this one, this is the point why we have that central region and then regions around it. Okay? Then for each region, we can, based on our truck capacity, we could just have 2 trucks finish each region. So then we just draw these loopy teardrop patterns, hitting all the customers in a loop. So from here you do hit a one loop and then do another loop. Okay. How many loops do you draw? How do you figure that out? Well, that is easy. You add up all the demand in a region. So you do 2 plus 1 plus 1 plus 1 plus 2. So you add up the total demand in a region. That's how many caskets you have to deliver. You look at your truck capacity. So because we divided the regions in a clever way, so our total demand is about constant in each region, we saw that we needed 2 trucks to be able to deliver that much. Okay, so you take the total demand for a region divided by the truck capacity. That tells you how many trucks you're going to need. So we got 2 trucks for each region because we split the regions in a way so there'll be equal demand in each region. Had we put these region here too, you might have needed 3 trucks for this one region and only 1 truck for that region. So that's why you have to split up a little bit carefully so you don't have extra trucks lying working one day and then being idle the rest of the week. So this way you hit each region one day of the week. You need 2 trucks total, and you can supply all of your customers in this region, and you can do it week after week. So this way you can save your distribution cost. Why? Because you have the minimum number of trucks required, only 2, and each truck is going to be doing a well-designed route each day of the week. So total distance traveled is being minimized and number of trucks is being minimized, so your costs are being minimized. Okay, let's look at the sweep method. Okay, so let me give you an example of the sweep method. This is another heuristic method to find routes. Just like nearest neighbor was 1, for TSP, the sweep method can work for multiple vehicles. The sweep method is very useful if all of your customers are kind of in a donut shape around you. So if you are in the center and your customers are in like a circle around you, then the sweep method is very efficient and very useful to make routes. All you do is you take a ruler and you draw a line wherever you want. It could be this line, any line you want. Then you sweep that line, and whichever customer you hit first, you visit that customer first. Then you keep sweeping. Whichever customer you hit second, as you sweep with that line, you hit that customer second, third, fourth. Then how do you know you have to come back after this customer? Because you're out of truck capacity. We have 4,000, 1 5,000, 3,000, that's 8,000 to 10,000. Our truck capacity is 10,000, so I cannot add this one to the same route. I have to come back. Once you come back, you start a new line and you start sweeping again. So we hit this customer first, we visit him first, then we hit this customer, we visit them, then we hit this customer, we keep sweeping, hitting customers until we're out of truck capacity. Again, truck capacity is a constraint, so we have to come back to the depot, draw a new line and start sweeping again. Okay? So in this course, I always want you to start at the 12 o'clock position and sweep counterclockwise so that your solution will match my solution. Okay, if you start at, 3 o'clock and sweep clockwise, you'll get different routes. In real life, there is no restriction. You can start anywhere and sweep in any direction. But for this course, always start at the 12 o'clock position and sweep left, looking at the page, or counterclockwise to make your routes. Okay? So hopefully it's clear how we made these routes by starting at this line and sweeping. If it's not clear, just try to do it yourself and see if you come up with the same routes as this picture. So print this slide and try to do this. Usually it's best to do it with a ruler. So you want to take a ruler here and then kind of turn the ruler counterclockwise and see which point you hit first. Without a ruler, it can be a little bit difficult sometimes. Okay, now let's do another algorithm. This is going to be our most involved algorithm, called the clock right algorithm, to solve the multi-vehicle routing problem. Now I'm going to give you an overview of this method in this lecture, and then I'm going to upload another video with a detailed example of this method that's going to go step by step. So get the big idea from this lecture and then go and watch the detailed example that I will upload on Blackboard to see all the detailed steps on how to use this algorithm. Okay. This is a very robust algorithm. It can generate a good to great solution. It is simple, can be done by hand or in Excel. It outperforms nearest neighbor, sweep, or eyeballed solutions, especially as number of stops grows. And it can often save you from having to buy expensive software. You can easily just hire a computer science student and tell them to code the algorithm into the computer for you. It's so simple. Or you can just make the routes doing your own computations by hand, like I will be showing you here. So this is the main idea of this algorithm. Okay? The algorithm's idea is this. We have to find a really good solution to this complex problem, and we don't know what good solutions, what is the good solution is. We don't know what it is. But we always know what the worst solution is to a routing problem. Okay? The worst solution that we can have is we start at a depot, our source point, we visit customer 1, and we come back to the depot. Then we start again, we visit customer 2, we come back. Then you start again, you visit customer 3, you come back. You visit customer 4, you come back. If you only hit one customer on each trip, that is the worst possible way to reach all the customers, because you're going to be traveling a whole lot of miles and mostly with an empty truck, because you're only hitting one customer on each route. So if you have 50 customers, you'll do 50 routes. Go customer 1, back from customer 1. Go to customer 2, come back from customer 2. That is the worst possible solution you can have. So the Clockright algorithm says, I don't know what the good solution is, but I do know what the worst solution is. It is to visit each customer on one trip and come back. So let me start at the worst solution and try to get as far from the worst solution as I possibly can. The further I move away from the worst solution, the closer I will get to the good solution. So that's the logic behind this algorithm. The logic is start at the worst possible solution and try to run as far away from the worst possible solution as possible. If you go really far from the worst possible solution, you're gonna end up in a good spot. It's gonna be some good solution. Okay? So how do we improve a solution like that? Let's say I have two customers, A and B, and I visit A, then I come back, I visit B, then I come back. How much do you travel? Well, you go from the depot, which is called 0 in this case, to A, so that's a distance of D0A. Then you come back a distance of DA0. Okay? Then you go to B, D0B, then you come back DB0. So the total distance is, this plus this plus this plus this. You add those 4 terms up. This plus this plus this plus that. These 4 numbers give you the total distance traveled in your worst possible solution. One way I can improve this solution is to go out of the depot and hit both A and B on the same trip. So if I go from the depot, I hit A, I go from A to B, and then I come back, then I've saved some distance. How much distance have I saved? Well, that is, we can look at that easily. My initial distance was D0A plus DA0 plus D0B plus DB0. Now D0A and DA0 are the same distance, because this algorithm assumes symmetry. Going from point A to B is the same as going from point B to A. That's not always true in real life based on traffic, and sometimes you have one-way roads which make it not the same. But for most practical purposes, going from A to B is the same as B to A in terms of distance and cost, approximately the same. So I can add these two up because they are the same. So I get 2 times distance between depot and A plus 2 times distance between depot and B for my bad solution. When I improve the solution by hitting both A and B in the same root, my distance becomes D0A plus dA to B plus dB0, where 0 represents my origin or my warehouse. If you subtract that distance from this distance, you get the savings, which is the difference in the two distances, which is how much distance you saved by doing this route versus the worst route. The savings are going to be D0A plus D0B minus DAB, because just this number minus this number. So when you subtract this number, you get a minus here, a minus here, a minus here. This minus stays here. These two minuses cancel out one of these two, and so you get D0A plus D0B minus DAB. That's the formula to calculate the savings that you get if you combine A and B on one trip. So instead of doing A and B separately on two separate trips, if you hit A and B on one trip, this is how much distance you save. Okay? So in the Clock-Wright algorithm, we calculate the savings for all possible pairs of distances, and then we try to pick the savings, try to maximize our savings. Okay? Can savings be 0? Yes. Think about this situation right here. So you have the depot. If point A is here, point B is here. If you go to A and you come back, and you go to B and then you come back, so you do two trips, that's the same distance as if you did one trip. You went to A, then you went to B, and then you returned. Okay? So whether you do A and B on one trip or two separate trips, there is no savings possible because A and B are on opposite sides of the depot. So it is possible to get a savings of 0 in some cases. Can savings be negative? Yes and no. In general, savings cannot be negative. The minimum they can be is 0 if the earth was flat and you were working on a flat surface. But because the earth is not flat, and sometimes there are one-way routes or shortcuts you can take in one direction, because of all these practical differences, you may end up with a negative savings as well. But don't worry, the algorithm works the same way. Whether savings are 0, usually they're going to be positive, or 0 or negative. You just rank the savings and the algorithm works in the same way. Okay? So the detailed steps are here. Let me just show you an example quickly to highlight how the algorithm works. So we have 10 points, 10 nodes. The first node is the warehouse or the depot, and nodes 2 to 10 are our customers, and we must deliver this much product to each customer. Okay? Our vehicle capacity is 23. Okay? So what we do is, in these algorithms, we usually have a table where you're given distance between any 2 points. So depot to node 2 is 25 miles, depot to node 3 is 43 miles, and you have all these distances in this triangle here. Okay? So then we calculate savings for every possible pair of points on this part of the matrix or the table. So 15 is the savings if you combine customer 4 and customer 7 on the same route. 0 is the savings if you combine customer 3 and customer 7 on the same route. So each of these on the top is the savings that we calculated using that formula. Notice that for savings to be there, you need 2 customer points. So there's no savings in combining depot and customer 2 because you need 2 customers, not the depot, not the warehouse. So their only savings are only defined when you have 2 customers you're combining on the same route. They're not defined for the depot plus customer because you need depot plus 2 customers. Okay? So the first step is we are going to sort the savings in a descending order. So what we see is that if we combine customers 6 and 10, we get the maximum savings. If you combine customers 9 and 10, you get the next highest savings. If you combine customers 8 and 9, you get the next highest savings, and so forth. So we start at the top and we start combining these customers onto the same routes to maximize our savings. Okay? So we're going to start with 6 and 10, and our first route is going to be customer 6 to customer 10. Okay, why? Because when I look at this pair of customers, I have not visited both of them. I have to visit both of them, so I just put them on a new route. Then when I get 9 and 10, I've already visited 10, but I can add 9 to the 10 because 10 is on the outside of the route. It's not an interior point. I can always connect to the edges of the route. So 10 was an edge of the route, so I can add 9 to it. So I factored in 9 and 10. Then you get 8 and 9. Well, 9 is on the outside of the route, so I can add 8 here. Okay, that's how you build routes. You have to keep in mind what's the truck capacity. That is 23. So I have to look at how much does customer 6 need, how much product customer 10 needs, how much product customer 9 needs, to make sure I don't exceed 23, which is my truck capacity. Okay? So we build routes like that. The slides take you through the details, and I am going to upload a separate video which goes over this example in detail. But the main idea is we calculate these savings using this formula. We put the savings in this matrix, then we sort them by descending order, and then we start taking off pairs of points from this list and start building our routes. That's the main idea behind this algorithm. Okay, so the detailed video going over step by step this example will be posted. Please learn how to do this algorithm. It's really important. On the homework, you'll also get a problem where you'll have to use this algorithm to make routes. Okay, and all the details can be found in the slides. Okay. So notice 6, 10, 9, 8 was our first route. We have hit a truck capacity of 23. So the next savings we find, we're going to start a new route. Okay? And our final solution is these two routes with these true loads for the truck. And that is the answer of the ClockWrite algorithm on how to do multiple vehicles with multiple routes to deliver or pick up product. That's all from this lecture. Please remember to watch the detailed working of this example that I'll upload in a separate video that will finish off the lecture. So this is like part 1 of the lecture in a way, and the detailed working of this example is part 2. So please watch part 2 of the lecture as well. I hope you learned something about distribution and routing today. This is a very important part of logistics because distribution costs can be very significant in terms of your total transportation and logistics costs.